Hello, this is the section 1.4 lesson. In mathematics, we like to take what's called the axiomatic approach to the study of new ideas. What that means is that we state a set of simple properties or rules that a new idea must follow, and then we build more complicated properties based off of those simple ideas. So in this section, we're going to state the axioms of probability and then use those to prove a few basic properties of probability. And one of those properties that we're going to prove is what's called the addition rule. So we're going to start off with what we call the axioms of events. And so we defined events in the last couple of sections. An event is simply a collection of outcomes. And here we're going to state some properties that the collection of all events must satisfy. So it says let S be the sample space of a random experiment. An event is a subset of S. We've already defined it in that way. Now it says let E be the set of all events. So this is a collection of a bunch of subsets. And we're going to assume that E satisfies the following three properties. So number one, the entire sample space is an event. Number two, it says that if A is an event, then its complement is an event. And again, this symbol here, A bar, denotes the complement of an event or of a set. And remember back from elementary set theory that the complement of an event is kind of, or of a set, is like the opposite of the set. We'll talk more about that here on the next slide. And then the third property says that if A1, A2, so on and so forth are all events, then the union of all those events is also an event. And so let's talk a little bit more about a complement. So here's just a simple picture to illustrate this. So this large rectangle, this is our sample space, so that's the collection of all outcomes. Here, this gray area, this is an event, so that's a collection of outcomes. And then this unshaded region, this is the complement. So it's everything that's inside of the sample space, but outside of the original event. Informally, the complement of an event is the opposite of the event. And we're going to see that complements play a very useful role in the study of probabilities. Okay, so now we're going to state the axioms of probability. These axioms are properties that we think every measure of probability should satisfy. These are not really definitions of the idea of probability. Rather, they're properties that probability as a set function must satisfy. So it says assume that for each event A, a number P of A is defined in such a way that the following three properties hold. First property says that that probability must be between 0 and 1 inclusive. Second, the probability of the entire sample space must equal 1. Informally, what this second axiom says is that the probability that something happens is 1. In other words, it's absolutely certain that something's going to happen. Third one's a little more complicated. It says that if we have a bunch of events, A1, A2, so on and so forth, for which AI intersect AJ is equal to the empty set for I not equal to J. So in other words, it says that if we take two events and they don't overlap or they have no elements in common, then the probability of A1 union A2, so on and so forth, is equal to the probability of A1 plus the probability of A2 plus so on and so forth. Okay? So if two events do not overlap, we say they are disjoint. This third axiom says that the probability of the union of disjoint events is simply equal to the sum of the individual probabilities. Okay? So to illustrate this third axiom, let's look at this example 141, and we're going to go back to this scenario where we randomly select a cube from a bag which contains 4 blue, 3 red, 2 green, and 1 yellow cube. Okay. Let's let G denote the event that we get a green cube, and Y denote the event that we get a yellow cube. Now, using the theoretical approach, the probability of G is 0.2, just 2 divided by 10, and the probability of y is 0.1. It's 1 divided by 10. Okay? Now, note that the event G and the event Y do not overlap. It's impossible to get a green cube and a yellow cube if we just select one cube from this bag. So G intersect Y is equal to the empty set. And so therefore, by the third axiom, the probability of G union Y equals P of G plus P of Y, which is 0.2 plus 0.1, which is equal to 0.3. Okay? So if we have disjoint events, it's very easy to calculate the probability of their union. Okay. Now, next we're going to prove a simple result or property of probabilities using these axioms. This is a very simple result, but very useful. Theorem 142 says the probability of an event plus the probability of its complement equals 1. Okay? And so to prove this, we're going to use some basic set theory and our axioms. Okay, so first, note that that A union its complement is equal to the entire sample space. And we can see why that's true if we just look back at that figure from a couple of slides ago. And also that A intersect its complement is equal to the empty set. So a set does not intersect its complement. So now using axioms 2 and 3, we have 1 is equal to the probability of the entire sample space. Well, that's equal to the probability of A union A complement. Well, what we have here are two disjoint events, and so by the third axiom, that's equal to P of A plus P of A complement. And so put it all together. 1 is equal to P of A plus P of A complement. So that's all there is. That's how we could use those simple axioms to prove a little more complicated result. Now, another version of this theorem is stated here at the bottom. It says that the probability of an event is equal to 1 minus the probability of its complement. So we've just algebraically rearranged terms in this theorem. Now, this version is useful because sometimes it's much easier to calculate the probability of the complement than it is to calculate the probability of the original event. And so that's illustrated here in this next example. So a fair six-sided die is rolled until the sum of the rolls is at least 11. Find the probability it takes more than 2 rolls. Okay? So that means we're going to roll it once, we're going to roll it again, find the sum of the rolls. If the sum is at least 11, we're going to stop. If not, then we're going to roll again and add that to the previous 2 rolls. If that's at least 11, we're going to stop. If not, we're going to keep going. And so we want to find the probability that it takes more than 2 rolls. Okay. Well, let's make an observation here. We could calculate it kind of directly. The probability it takes more than 2 rolls. Well, more than 2 rolls means it takes 3 rolls, or 4 rolls, or 5 rolls, or 6 rolls. It's not going to take any more than 6. Now, those different events there, 3 rolls, 4 rolls, 5 rolls, 6 rolls, those are disjoint. It's impossible to take exactly 3 rolls at the same time that it takes exactly 4 rolls, so on and so forth. So using the third axiom, we could calculate the probability of 3 rolls plus the probability of 4 rolls, so on and so forth. So I could, in principle, calculate each one of these individual probabilities, add them up, and I'm all done. But that's 4 different probabilities to calculate. I don't want to have to do all that work. So we can simplify our work by using complements a little bit. So let's make an observation here by our theorem that we just stated. The probability of 2 or more rolls is equal to 1 minus its complement. Well, the opposite of more than 2 rolls is 2 rolls or fewer, right? And but now if we think about it, 2 rolls or fewer, that means 2 rolls or 1 roll or 0 rolls. But we can't get a sum of at least 11 in 0 rolls or 1 roll. So this is really 1 minus the probability of 2 rolls. So now all we need to do is calculate the probability of getting a sum of at least 11 in 2 rolls. Okay? Well, to do this, we can use some results back from a couple sections ago where we created this table. So here, this table represents the sample space from the roll of 2 dice. We could think of this as like the first roll of this die and then the second roll of this die. And then here are all the possible sums from those 2 rolls. So we want to know what's the probability of getting at least 11 in these 2 rolls. Well, if I look here in my table, I see that I've got only 3 outcomes for which the sum is at least 11. So the probability that's going to take exactly 2 rolls is 3 over 36. And so then we take 1 minus that to get 11/12. And so there we go. There's our final answer. The probability that's going to take more than 2 rolls is 11/12. So there we go. We see that calculating the probability of the complement was relatively simple, much easier than calculating the probability of the original event directly. So this example illustrates the usefulness of complements. Now next we're going to state a rule that we can prove using the axioms, and it's done in the book, but we'll just state the result here. This is what we call the addition rule. The addition rule is kind of an extension or a generalization of axiom 3. Axiom of 3 applies only to disjoint events. This addition rule applies to non-disjoint events. Okay? So this rule says the probability of A union B is P of A plus P of B minus the probability of their intersection. Now, you may ask, why do we have to subtract? Well, the basic idea here is we subtract so that we don't double count anything. So to illustrate what this means and how to use the addition rule, let's look at this last example. So what we have here in this table at the bottom is the results from a professor who gives his students some review problems to do before a test. Hey, that sounds kind of familiar. And each student either completes the problems or did not complete the problems. And this table tells us that 42 students completed the problems, 38 students did not complete, for a total of 80 students. Okay? Now, the students took the test, and the professor recorded what everybody got. A total of 46 people got an A or a B, and a total of 34 people got a C or below. The numbers in the middle of the table tell us that 34 students got an A or B and completed the problems. 8 students got a C or below and completed the problems. 12 students got an A or B and did not complete, and so on and so forth. Okay. So what we're going to do here is randomly choose a student from this group of 80. And let's let E denote the event that the student did not complete the problems, and F denote the event that the student got a C or below. We want to calculate the probability of E or F, E union F. Okay. So let's look at one right way that we could do this problem. And we could take the theoretical approach. We have a finite sample space. Everything is equally likely, so the theoretical approach applies. So E union F is the same as saying a student did not complete the problems or got a C or below. And so what we could do is simply count the number of students who did not complete the problems or got a C or below, and then divide that by the total number of students. Well, the total number of students is 80, so that part's easy. Okay. Now to get the numerator, we got to look through the center of the table and count the number of students who got a C or below or did not complete the problems. So if we look here, these 34 students, they completed and they got an A or a B. So we're not interested in those students. These 8 students got a C or below. So we're interested in those, so we're going to count those. These 12 students did not complete, so we're going to count them. And these 26 students did not complete. They also got a C or below, so we're going to count them. And so the total is 8 plus 12 plus 26. We divide that by 80, and we get our final answer of 0.575. So there's one right way to calculate this probability. Okay. Now let's look at a wrong way to do it. What we might be tempted to do is to use axiom 3 and say that, well, union means addition. So let's calculate the probability of E. Probability of E is the total number of students who did not complete the problems divided by 80, so 38 over 80. P of F is the number of students who got a C or below, 34 divided by 80. And so then we just want to calculate or add those two probabilities together to get 72 over 80, which is 0.9. But the problem here is that this number double counts these 26 students who got a C or below and did not complete the problems. So we don't want to do that. We don't want to double count those. So another right way to do it is to use the addition rule, where we calculate these probabilities P of E and P of F just like we did before. But then we also need to calculate the probability of the intersection. So we take 26 students who did not complete and got a C or below, divide that by 80, and then we add and subtract to get 46 over 80, which is 0.575, which is the exact same answer we got using the theoretical approach.